Meteoroids are small rocky or metallic bodies that travel through space, often originating from comets or asteroids. Despite their prevalence, the term meteoroid is frequently misunderstood and inconsistently defined across different languages and scientific communities. In some contexts, meteoroids are described simply as any object in space that is smaller than an asteroid, while other definitions specify particular size ranges or origins. This inconsistency can lead to confusion when discussing related phenomena, such as meteors and meteorites. Understanding the precise meaning of meteoroid is essential for clear communication in astronomy and planetary science. A meteoroid is a small fragment of rock or metal that travels through space, often originating from comets or asteroids. When a meteoroid enters Earth's atmosphere, it heats up due to friction, producing a bright streak of light commonly known as a shooting star or meteor. If the meteoroid survives its fiery descent and lands on Earth's surface, it is then called a meteorite. The journey from space to Earth is perilous, as most meteoroids burn up before reaching the ground. The distinction between these terms lies in their location. Meteoroids are in space. Meteors are the visible streaks in the atmosphere, and meteorites are the remnants that reach the surface. This process helps scientists learn more about the composition of our solar system and the dynamic interactions between celestial bodies. Chondrites are a class of meteorites that are among the oldest and most primitive materials in our solar system. They are characterized by the presence of small, round particles called chondrules, which formed from molten droplets in space billions of years ago. Meteorites are generally categorized into three main types: stony, iron, and Stony-Iron. Chondrites fall under the stony meteorite category and are distinguished by their granular texture and lack of significant metal content. Their origins trace back to asteroids that never underwent melting or differentiation, preserving the early solar system's building blocks. In contrast, iron meteorites originate from the cores of differentiated asteroids and are composed mainly of metallic iron and nickel, while Stony-Iron meteorites contain a mix of silicate minerals and metal. The physical characteristics of these meteorites, such as density, color, and structure, provide valuable clues about the processes that shaped our solar system. Impact craters and fragments scattered across planetary surfaces offer compelling evidence of meteoroid collisions throughout our solar system. On the Moon, these craters are especially prominent, with some dating back billions of years, due to the lack of atmosphere and geological activity that would otherwise erase them. Mars also displays a wide variety of impact features, ranging from small pits to massive basins like the Hellas Planitia. The presence of ejecta, or fragments thrown out during impacts, further reveals the dynamic history of these celestial bodies. By studying these scars, scientists gain valuable insights into the frequency and scale of meteoroid impacts, as well as the composition and evolution of planetary surfaces. These remnants serve as natural records, helping us understand both the past and ongoing processes shaping worlds beyond Earth. Meteorite impacts are a global phenomenon, with confirmed sites found on every continent. To date, thousands of meteorite finds have been documented worldwide, ranging from small fragments to massive craters. Notable impact sites include the Barringer crater in the United States, the Chicxulub crater in Mexico, and the Tunguska event area in Siberia. Scientists have cataloged over 60,000 meteorite specimens, each contributing valuable data to our understanding of these cosmic visitors. The widespread distribution of meteorite finds highlights the frequency with which meteoroids collide with Earth. These impacts vary in size and effect, but collectively, they underscore the planet's ongoing interaction with objects from space. Identifying meteorites involves a careful examination of several key characteristics. Visually, meteorites often display a dark fusion crust formed as they pass through Earth's atmosphere and may show unique surface features like regmaglyphs, which resemble thumbprints. Their weight is typically higher than ordinary rocks due to dense metal content, making them feel unexpectedly heavy for their size. Magnetism is another clue, as most meteorites contain iron and will attract a magnet. Chemical analysis can confirm the presence of elements such as nickel, which is rare in terrestrial rocks, but common in meteorites. Experts recommend combining these methods for accurate identification, as no single test is definitive on its own. The Willamette meteorite is one of the most remarkable meteorite discoveries in the United States. Weighing approximately 15.5 tons, it is the largest meteorite ever found in North America, and the sixth largest in the world. Composed primarily of iron and nickel, its surface features deep cavities formed by centuries of exposure to rainwater. Discovered in Oregon in 1902, the meteorite holds cultural significance for the indigenous Clackamas people, who regarded it as sacred. Its unique composition and history have made it a centerpiece for scientific study and public fascination. Today, the Willamette meteorite is displayed at the American Museum of Natural History in New York, where it continues to inspire curiosity about the origins of our solar system. Meteorites are often identified by their unique chemical composition, particularly their high concentrations of iron and nickel. These elements are present in much greater abundance in meteorites than in most terrestrial rocks. Scientists use techniques such as spectroscopy and X-ray fluorescence to analyze the elemental makeup of suspected meteorite samples. By comparing the ratios of iron and nickel, researchers can distinguish meteorites from Earth rocks, which typically lack significant nickel content. Additionally, the presence of certain minerals, like troilite or kamacite, further supports a meteoritic origin. These analytical methods provide reliable ways to confirm the extraterrestrial nature of meteorite specimens. When you come across a rock that you suspect might be a meteorite, seeking expert appraisal is crucial. Professional verification ensures that your find is accurately identified, as many terrestrial rocks can closely resemble meteorites. Experts use specialized tools and knowledge to analyze features such as density, magnetic properties, and surface characteristics. Relying on professional assessment helps avoid misidentification and provides valuable scientific information if your specimen is genuine. Meteorite identification is a complex process, and only trained specialists can confirm authenticity with confidence. By consulting experts, you contribute to scientific research and ensure your discovery is properly documented. Meteoroids have played a significant role in shaping the Earth's surface and its history. When these space rocks enter our atmosphere and collide with the planet, their immense energy can cause catastrophic destruction. One of the most notable events was the impact that created the Chicxulub crater in Mexico, widely believed to have contributed to the extinction of the dinosaurs around 66 million years ago. Other major impacts include the Tunguska event in Siberia in 1908, which flattened thousands of square kilometers of forest, and the Barringer crater in Arizona, formed about 50,000 years ago. These events serve as reminders of the unpredictable and sometimes devastating influence meteoroids can have on our world. Scientists continue to study impact sites to better understand the frequency and consequences of such collisions. The Vredefort Dome, located in South Africa, is recognized as the largest confirmed impact crater on Earth. Formed over 2 billion years ago, this immense structure was created when a massive meteoroid, estimated to be about 10 to 15 kilometers in diameter, struck the planet. The force of the impact released energy equivalent to millions of nuclear bombs, reshaping the landscape and leaving a circular depression that spans nearly 300 kilometers. Over time, geological processes have eroded and altered the crater, but its core features remain visible. The Vredefort Dome offers scientists valuable insights into planetary impacts, Earth's early history, and the processes that shape our planet's crust. Its study has helped refine our understanding of impact events and their role in geological evolution. Approximately 66 million years ago, a massive asteroid struck the Earth near what is now Chicxulub, Mexico. This impact created a crater over 180 kilometers wide and unleashed energy equivalent to billions of atomic bombs. The collision triggered wildfires, tsunamis, and sent vast amounts of debris into the atmosphere, blocking sunlight and drastically cooling the planet. As a result, ecosystems collapsed and food chains were disrupted on a global scale. Scientists believe these catastrophic changes led to the extinction of nearly 75% of all species, including the non-avian dinosaurs. The Chicxulub impact remains one of the most significant events in Earth's history, reshaping life and paving the way for the rise of mammals. The Hoba meteorite holds the distinction of being the heaviest single meteorite ever discovered on Earth. Located in Namibia, this remarkable space rock weighs approximately 60 tons. Its composition is primarily iron, with traces of nickel and other elements, giving it a metallic appearance and exceptional density. Scientists believe the meteorite landed on Earth around 80,000 years ago, but it was only uncovered in 1920. Due to its immense size, the Hoba meteorite has never been moved from its landing site. Today, it is recognized as a national monument, attracting visitors from around the world who come to marvel at this extraordinary relic from outer space. The Barringer crater, located in the Arizona desert, stands as a remarkable testament to the power of cosmic impacts. Formed approximately 50,000 years ago, the crater was created when a large iron meteorite, estimated to be about 50 meters in diameter, struck the Earth at a speed of nearly 12 kilometers per second. The force of the impact released energy equivalent to about 10 megatons of TNT, instantly vaporizing the meteorite and excavating a massive hole in the ground. The resulting crater measures roughly 1.2 kilometers across and 170 meters deep. The devastation extended well beyond the immediate impact site, flattening trees and altering the landscape for miles around. Today, the Barringer crater remains one of the best-preserved meteorite impact sites on Earth, offering valuable insights into planetary geology and the effects of extraterrestrial collisions. In 1908, a massive explosion occurred over the remote Tunguska region of Siberia, flattening over 2,000 square kilometers of forest. The blast was so powerful that it knocked people off their feet hundreds of kilometers away and produced atmospheric effects detectable around the globe. Despite its magnitude, no impact crater was found, fueling speculation about its cause. Scientists have long debated the origin of the event, with leading theories suggesting a meteoroid or comet exploded in the atmosphere before reaching the ground. Ongoing investigations continue to analyze soil, tree rings, and eyewitness accounts to unravel the mystery. The Tunguska event remains one of the most intriguing natural phenomena of the 20th century, offering valuable insights into planetary science and the potential hazards of near-Earth objects. In February 2013, the Chelyabinsk meteor entered Earth's atmosphere over Russia, exploding with a force equivalent to about 500 kilotons of TNT. The shockwave shattered windows, damaged buildings, and injured over 1,500 people, primarily due to flying glass. This unexpected event highlighted the vulnerability of populated areas to meteoroid impacts. In its aftermath, scientists intensified efforts to monitor and track near-Earth objects, developing improved detection systems and international collaboration protocols. The Chelyabinsk incident underscored the importance of early warning systems and public education on how to respond to such threats. Today, ongoing research aims to better predict and mitigate the risks posed by meteoroids, ensuring greater preparedness for future events. In summary, meteoroids are small fragments of rock or metal that travel through space, occasionally entering Earth's atmosphere. Their identification relies on careful observation and analysis, distinguishing them from other celestial objects. Throughout history, meteoroids have played a significant role in shaping our planet, leaving behind craters and contributing to scientific discoveries. The study of these objects has provided valuable insights into the origins of our solar system and the dynamic processes at work in space. By understanding meteoroids, scientists continue to unravel the mysteries of Earth's past and the universe beyond.